following. So in this case over here, you've got benzoic acid and sodium benzoate. So the very first thing that you guys want to do is you want to take a look at your data booklet. And so one of the things that you want to do is take a look at what this benzoic acid and sodium benzoate is. And so if you take a look, you should be able to see it, if I can find it, right over here, benzoic acid, right? And then in this case, the negative ion or the polyatomic ion is benzoate. And so this comes from the naming rules you guys learned when you guys were in grade 10. So this equation is the equation that you're looking for, and this is now where you guys find your Ka. So with respect to this, when you guys are doing your calculations, one of the things that I will say is you can actually do this equation starting with either the weak acid or the conjugate base, okay? And the reason here is that sometimes I may ask you a question and I'm giving you the amounts of the weak base and not the conjugate acid. So what I'm going to do for this first one is I'm actually going to do this in both directions. So you can see that it's achievable either way, okay? So right over here, if I take a look, my benzoic acid is C6H5COOH plus H2O in equilibrium with C6H5COO minus plus H3O plus. So I jumped through a couple of considerations being, what am I working with? So over here, you take a look at the following. I am working with benzoic acid that I saw in my data booklet right over here. And so now if I take a look at my corresponding salt, notice my corresponding salt over here is NaC6H5COO. Yes? And so you can probably already say, I can just get rid of the Na because I know it comes from the NaOH. And therefore, it will not react with the water. So this is now the steps that I have taken. And then now I'm just going to go with the ICE. And so in terms of where the ICE is concerned, what I'm going to do is I'm just going to put down 0.12 molar and 0.20 molar and nothing here. This is minus X plus X plus X, 0.12 minus X, 0.20 plus X, and X. And we know that the pH is established once the system has reached equilibrium. Now that I've done this, I know that since I have acid forming, I'm going to have Ka is equal to C6H5COO minus times H3O plus all over C6H5COOH. And then so now I go back into my data booklet right over here, and it's 6.5 times 10 to the power minus 5. So I'm going to go 6.5 times 10 to the minus 5 is equal to X times 0.20 plus X times X all over 0.12 minus X. Given the relative size, I can say that this is very small, this is very small. And so now if I solve for X, 6.5 times 0.12 divided by 0.20, I get 6.5 times 10 to the minus 5 times 0.12 divided by 0.2, I get 3.9 times 10 to the minus 5, which is the concentration of hydronium. So pH over here is negative log 3.9 times 10 to the minus 5. And if I was to do that, I end up with 4.41. Does this look very familiar? Does this comfortable? So now if I do it the other way, of course it is going to be a more challenging and it's going to involve more steps. But in part, what I'm interested in is that you have the skill set to be able to solve whatever I throw at you, right? So the whole idea is I don't care that you memorize one system, but if you cannot navigate another problem that you've never seen before using the processes you've learned here, then you really haven't learned much. You just learned to memorize something. So in this case, here I am now going to start with my conjugate base first. So C6H5COO minus plus H2O in equilibrium with C6H5COOH plus OH minus. I'm now going to have my ICE right over here. And in this case over here, you've got your 0.20, 0.12, and then you have your 0, minus x, plus x, 0.20 minus x, 0.12 plus x, and x. Now, of course, I have a hydroxide being formed, yes? So therefore, what am I using? Ka?
KB.
I'm using Kb. So Kb over here is C6H5COOH times OH minus all over C6H5COO minus. So we know that the Kb is 1.0 times 10 to the minus 14 all over 6.5 times 10 to the minus 5. So if I was to put this in my trusty calculator, I end up with 1.5 times 10 to the minus 10. So now I go 1.5 times 10 to the minus 10 is equal to 0.12 plus x all over 0.20 minus x. And again, I'm going to say this is very small and this is very small. So now I'm going to go times 0.2 divided by 0.12. And so now I have x is equal to 2.6 times 10 to the minus 10, which is the hydroxide. So POH is negative log 2.6 times 10 to the minus 10, which is equal to 9.59. So pH over here is 14.00 minus 9.59. And again, I get 4.41. Now, when you guys are looking at this, make a note that you end up with the same answer. Now, why is it that you guys want to do this? Because sometimes when you guys set it up and it is your acid reaction, you might not be able to get an equation that makes sense. Okay? So therefore, being able to use one or the other variation, you should be comfortable with that. Okay? Now, let's take a look at this next one. Now, this next one is a little bit different because you're finding initial. So over here, I have my NH3, which I recognize as my weak base. Over here, I have my salt. So right there and then, I take a look. Which one is going to react with the water? NH4 or the Cl? The NH4 will react with the water because you know that the Cl comes from HCl. So do you see how we're building on those skills, right? So these are the considerations that need to take place before we go ahead and generate our predominant equation. Now you might say, okay, I have two choices. So if I don't know how many moles, I might put this in the product. So at this point, I'm going to go NH4 plus H2O in equilibrium with NH3 plus H3O plus. And I'm going to have my ICE. Now it says how many moles of NH4? That means I don't know how much NH4 is here. But I do know that I have 0.10 molar here, don't I? And then I have 0 here. So what do I do now? Like, I know that it's going to shift to the right, but how much is it going to shift to the right by? So do I say, oh, minus y plus y, and go from there? If I do that, I'm in trouble because I only have one equation and two variables. So what piece of information is there that will help me? Okay, so thank you, Rihanna and Gia. The pH. Remember that the pH is established at equilibrium. If it wasn't established, then your pH is going to be going up and down until it stabilizes, right? Because remember, parallel lines. So this is 9.00, so this is 10 to the power of minus 9.00. So I'm going to fill in the rest. So this is plus 10 to the power of negative 9.00. This is plus 10 to the power of negative 9.00 minus 10 to the power of negative 9.00. So this is x minus 10 to the power of minus 9.00, 0.10 plus 10 to the power of negative 9.00. So now once you do this, you go Ka is equal to NH3 times H3O plus all over NH4. And I get 5.6 times 10 to the minus 10 is equal to 0.10 plus 10 to the power of 9.00 times 10 to the power of negative 9.00 all over x minus 10 to the power of minus 9.00. And then we put it into our trusty calculator. And I end up with x is equal to 5.4 times 10 to the minus 4. What? Really? Okay, my calculator work is awful. Ah, there we go. I got 0.18 moles per liter, or molar. So if I want to find the number of moles, it's 0.18 moles per liter times 1.0 liter, so 0.18 moles. Did you guys get that? Okay, now, one last concept about buffers that I want to cover with you guys is called buffering capacity. Okay, so I am going to just grab it from my last class. And I would like you to write this down. Buffering capacity is the ability or the extent that a buffer can resist change in pH.
What? Oh. The what? Buffer capacity.
Right.
What now? Sure.
Huh? The buffering capacity, the ability / extent that the buffer can resist change in pH.
How's that going?
What do we mean by
This
that?
is changed in pH.
So let's pretend I have two buffers. And I'm going to say this buffer is made from 0.1 molar and 0.1 molar of my weak acid conjugate base. This one is made from 1 molar and 1 molar of my weak acid conjugate base. Which one is better? So if you take a look here, both of these are made from the same pairing, yes? So therefore, it has nothing to do with the identity of the material creating the buffer. Buffering capacity has everything to do with how long it takes before it is unable to buffer anymore. So for example, if you take a look at this one, notice that this is 10 times less than that. So if I had a beaker over here, and I have a CH3COOH /CH3COO minus pairing, and then over here, I have a CH3COOH and CH3COO minus pairing. This one's 0.1 molar, that means I have one of each here. This one is 1 molar, then that means it's 10 times that. So now let's pretend that I'm going to take a bottle of NaOH. I'm going to put 1 drop of NaOH in here. This goes down. Equilibrium is now going to shift to the right, yes? But it's going to involve using up that CH3COOH. So it's now compensated. Now what if I put in a second drop? Will there be any more of the weak acid to try to replenish the hydronium ion? And the answer is no, it's reached its limit. It's reached its buffering capacity because beyond that, the second drop, the pH is now going to shoot up. Right? Do you remember like when you did your titration curve, that part where it shoots up? However, if I take a look at this one, and now I have my NaOH right over here, and I put in 1 drop of NaOH, well, this one's gone, so I just basically replenish it with 1. I still have 9 left, don't I? So I'm going to put in another drop. Oh, that one's gone because it's now trying to replenish the hydronium ion. Then I do another one, and then another one goes. And then, so what do you notice about its ability to absorb the extra acid that's being put into the solution? It's able to absorb more, right? So just like when you guys learned in biology about buffers, the buffers in your blood can only buffer so much before you actually are unable to buffer anymore, and then your pH is now disrupted. Right? So with regards to this one here has a larger buffering capacity because the concentrations are higher. That means you have more resources on either side to be able to adjust for the disruptions in the pH. Does that make sense to you guys? Questions? Clear as mud? Okay. So let's move on to the next part. Now this one here is a metal oxide, and so in this case over here, don't flip, but what I would like to do is I want to point back to when we talked about strength of bases. So do you guys remember this page where we talked about strong bases? Do you remember that? Now down here, do you guys remember I just said don't worry about this part? We are going to worry about it later on in the acid and base. So we're now talking about this. Okay? So now going back into the notes over here, now take a look. We're looking at metal oxide. So when metals react with oxygen, you form metal oxide. Now the key part over here is that you have a metal and you have a non-metal. So essentially this is an ionic compound. Now where this is concerned, when you first take a look at it, you know that with an ionic compound, it should theoretically dissolve in water. And you did this in solubility. And you know this because when you take a look at Na, and if we were to go into our data booklet, remember in solubility, you learned that anything that is connected with the alkali ion, it will be soluble. Yes? So what I'm going to try to do is I'm going to try to explain how Na2O plus H2O is going to give you NaOH. Where did that come from? So the first thing that you need to note is anytime you have a metal oxide, it will always form something that is basic. Okay? So that is what we're going to be working with in Chem 12. So in this case, where did the basic hydroxide come from? So the first thing that we want to take a look at is, this is a metal oxide, so when it dissolves in water, it dissociates to become 2Na plus and an O2 minus. Does this bring back good memories of solubility? Now, where Na is concerned, you know it's not going to do anything. But if you look at the O2, and you look at your data booklet right over here, down at the very bottom, I want you to see this O2, which is right here in your data booklet. Do you see that it is way down here at the bottom of your list? It's under the column of a base. Do you guys see that? And then if you look down here on the list, notice that this is a very strong base. That means the O2 minus wants to get an H plus and forms OH minus. So now when you go back into your notes over here, the Na2O dissociates to form 2Na plus and the O2 minus. The O2 minus wants to get an H plus. Where is it going to get it from? From water. So now you have H2O over here. Now I'm going to change this. So now I'm going to have H, and then this is OH. Do you see that? So now it's going to pull off an H, and now you're going to get OH minus plus OH minus. Do you guys see that? So if I was to now add them like we did in reaction mechanisms, the O2 minus crosses out, doesn't it? So now what do I have? Na2O plus H2O giving you 2Na plus 2OH minus. Do you see that? And what does that become? 2NaOH. So do you guys see it forming something basic? So all that I care about for this is that you recognize that it is going to form something that is basic. Now for this one over here, when you have a non-metal and an oxygen, it's going to have a non-metallic oxide. And what I need you guys to remember is that it is going to form something that's acidic. And you're like, how do we know? You don't. You just need to know that. So one of the few things I want you guys to memorize. Now why is it that it doesn't have the same reaction as the metal oxides? It's because you have a non-metal and a non-metal. What do two non-metals form? A covalent. So this is a covalent compound, and you know that the nature of a covalent compound is different from an ionic one, yes? They share electrons rather than exchange. So as a result, they are not going to break apart, and they will in fact combine with water to form something acidic. Okay? So I'm going to show you the differences here. have some water, and remember a universal indicator, green means neutral. Okay, so I'm just gonna split this up into two, so you have a reference. There we go. Now, what I'm gonna take out is calcium oxide. So do you see on my list under metal oxide, there's the calcium oxide under sodium oxide. Do you see that? Okay, so what I'm gonna do is I'm gonna pour some in here. And then I am going to stir this around. Now, when you guys work with your universal indicator, what color does it turn when it gets basic?
Purple, blue.
Okay, so do you see it's beginning to turn purple? Do you see it's kind of a bluish color, right? So this is now turning purple because the calcium oxide is now dissolving and the O is now releasing to form hydroxide, and then you now have a more basic solution. Okay? Now, what we want to do is we want to take a look at carbon dioxide. So with the carbon dioxide, it's supposed to form something acidic, carbonic acid. Okay? How many of you guys have a soda stream at home? Yeah. So I'm going to demonstrate this to you with a local source of carbon dioxide. Where do you think this local source of carbon dioxide is going to come from?
Breathing.
Breathing. Okay, so here's your green.
Yo. That is a very long breath. That's pretty impressive. That's impressive. I don't think I could do that. Not so dumb. Accidentally drink. Don't laugh.
That's why I became a teacher. Got lots of hot air. So, what color did this turn?
Yellow.
Yellow. So if you look down here, the pH has gone down. Okay? So this is just a demonstration. One turned purple, so you see how it's purple here? And then this one kind of turned that sort of yellow color, so it is acidic. So with this, where this is concerned and where the application is that here we're going to talk a little bit about acid rain. Now, a lot of you guys have probably heard about acid rain, but the question is, nobody ever told you really where it came from. So with that in mind, there are two sources of acid rain. First source is something from nitrogen, so nitrogen oxide and sulfur oxide. So these two here are sources of acid rain. And the reason why they are sources of acid rain is because they are generated by some sort of a human mechanism. Okay? Like machinery or whatever it is. It's kind of artificially made. Okay? In large quantities. Now, in this case over here, when you take a look, you might say, well, where does the NO or NO2 come from? And oftentimes it actually comes from you guys just driving back and forth from home to school, or you go downtown. And you might say, well, what do you mean by that? So in this case, I want you to think about your dream car. Who would like to own this lovely car? Somebody said this looked like a toenail, but anyways. Who would like to be the owner of this beautiful car? Brianna, okay. Okay. Now, you guys all know that she will go to her local gas station and gas up with octane, so C8H18 plus O2, and she's going to then burn it to form H2O and H2O, your typical combustion reaction. So you know that you fill it up, and then you're supposed to now feed it into your engine, and it's supposed to burn, and then out of the tailpipe will only come CO2 and H2O, and so really it's not that bad for the planet. Now you know the gas comes from the gas tank. Where does the oxygen come from? It comes from the air. Now is the air made from 100% oxygen? No. What is the air made up of? Nitrogen, which is 80%, and oxygen, which is 20%. So in this case, when the air is fed into your engine, the engine, first of all, they try to make it burn efficiently. So that means they try to increase the compression and the temperature at which the gasoline combusts. So as a result, what happens is that higher pressure and higher temperature is not only going to react with the oxygen, but it will react with the nitrogen. It does not discriminate about which one. So in addition to CO2 and H2O, it will also now spew out NO2 and NOs. So in Vancouver now, I do all of the sky rises over here, and then we have our pristine mountains in the back. You are now letting off a whole bunch of NO2. I'm going to use orange here because that is what NO2 colors are. Are we okay with that? Now, you also know, fortunately or unfortunately, that Vancouver experiences a lot of rain. So what ends up happening is that when it rains, the water droplet is going to fall through this layer of NO2 and NO and combine. And when they combine, this is when they form HNO2, which you know is a weak acid, but at the same time, it can also form HNO3, which you know is a strong acid. This is one of the reasons why a lot of your buildings have rust on it. This is why your cars, within a very short time, develop rust, because acid is actually contributing to its corrosion. You might say, oh, no problem, I have never seen the NO2. So if I was to go into Google right now, and I look at smog over Vancouver, and we look at images, have you guys ever seen sort of this orangey layer that is above Vancouver sometimes? That's your NO and NO2. Okay? Now, you might say, well, I don't really care because we live by the coast, and so we have all of this onshore breeze. When it's an onshore breeze, then you know what? It just blows the NO2 and the NO away, and then so we have now our beautiful sky. But it has to go somewhere, doesn't it? So it gets blown into the interior, and then it ends up here, between the mountains. What is that area called between mountains? It's a valley. And what's the closest valley next to us? The Fraser Valley. So the poor Fraser Valley gets all of our polluted air. This is one of the reasons why in the Fraser Valley they always get air quality warnings. Because all of the pollution gets blown inland, and they are the ones that actually have to deal with it, because we never deal with it because it all just gets cleared away. Okay? So, next time you drive your car, think about the poor Fraser Valley people. Okay? Now, the same thing is for the sulfur oxides. Now, in terms of oxides, again, it comes from burning fossil fuels. Now, this has a bit of an economic sort of issue for Canada. Now, for us in BC, it's not so much because we rely on our forests. But our neighbors next to us in Alberta, a lot of their revenue comes from their tar sands. So they actually have tar sands, which what they do is they try to drill out the petroleum products and they sell it off. This is one of the reasons why Alberta is so rich, right? But their economy is very dependent on gas prices, so it's up and down based on the gas prices. However, the problem with the Alberta tar sands is that it takes a lot of refining because the tar sands contain a lot of sulfur. Therefore, because of having so much sulfur, it takes a lot longer to actually remove it. So as a result, if you were a company and you were trying to burn some of the fuel from the tar sands, when you burn this, you're now going to combine sulfur with oxygen and you're going to get SO2 or possibly SO3. And guess what happens again is that if it rains and water drops through, what is it going to form? H2SO3 and H2SO4, which is a corrosive acid. So this is why the US does not want to buy this oil from Alberta, because it's known as dirty oil. Okay? So, in this case, you might say, well, what about carbon dioxide? This is not acid rain. And the reason is because carbon dioxide exists naturally in the environment. Like you and I are breathing it out right now. So that is not causing acid rain. Right? The plants are also breathing it out at night when they are unable to photosynthesize. So this will cause your solution to become slightly acidic. So my yellow color is a pH of 5. But it is not going to bring it down so much that it is now corrosive to the land. So what if we now have acid rain? How does it affect us? So right now, our oceans are a huge reservoir buffering the acid rain that is coming down. But what ends up happening is, as more and more acid rain comes down, eventually the pH of the oceans is going to be impacted. So therefore, a lot of the organisms are going to now die off. So you're going to begin to see a drop in things like plankton. And you might say, well, who cares about plankton? The reason why you should care is because plankton on the food pyramid is the lowest rung, right? It is the food based on every single other tier is going to be based on. So if your plankton is now going to disappear, then the larger crustaceans are going to disappear, so the larger fishes are going to disappear, and then so on and so forth. Once you reach 5, then pretty much all the plankton is gone. And then you're now going to have a loss of fish population. Just to let you know, salmon is very sensitive to pH. So if you actually now start losing salmon, say bye-bye to sashimi. No more sashimi for you, Alina. And then in this case over here, once you get rid of all of this, it is going to affect things like your front lawns. How many of you guys have a front lawn in your place? If you guys take a look, rarely has it ever got grass on it. It's got moss. The reason why it has moss on it is because our rain is very acidic. That's why at the very beginning of the season, you are told, or your parents might be told, you need to lime your lawn. Why lime it? Because you're supposed to neutralize the soil. So with regards to this unit has now formed the basis of some of the applications for you, right? You guys are learning more about the environment, and you have learned the mechanics of the environment. Okay, so some of you guys, as you take a look out, the next time you order sashimi, just think, I'm so happy the pH in our oceans is still normal. Sean goes, my teacher's weird. Okay, so we are now officially done. And nobody claps, okay? So. Sean Kim.
Oh.
So,
Uh-oh.
here